Hello, this is Professor Kuehn, and welcome back to my lectures on astronomy at Wisconsin Lutheran College. For the past 6 or 7 weeks, we've been extensively reading the works of many geocentrists, that is, people who believe that the Earth itself resides at rest at the center of the universe. We've been studying the works of Aristotle and Ptolemy, Waldseemüller, Bede, and others. And hopefully over the course of the last 6 or 7 weeks, I've converted you into a thoroughgoing geocentrist. Now what we're going to do in the second phase of this course is question this worldview. We're going to be starting with the work of Nicholas Copernicus, who was born in 1473 in a German-speaking area of what is now Poland. It's called the city of Torun. He was a physician, a doctor, and he was also a political advisor of the Bishop of Ermland, who was the bishop of the principality in which he lived. He did a number of things. He was an advisor to King Sigismund I of Poland. He wrote a treatise on the evil of inflation, that is debasing coinage. So they would take coins that were made of gold, let's say a 1-ounce gold coin, and many of the governments at the time would then melt these down and make them into gold coins that were only, let's say, 0.8 ounces of gold and the other 0.2 ounces of some other material. And they would keep that extra gold for themselves. It's much easier, I guess, when you have paper money to debase the value than with coins, but nonetheless, that kind of debasing of coinage was happening at the time as well. And Copernicus was very opposed to this kind of thing. He said it was an evil thing to do. Another thing that he did as an astronomer, he advised the Lateran Council for calendrical reform. That is the council that dealt with the issue of many issues, but one of them was how to deal with the church calendar. And his advice, Copernicus' advice, informed many of the decisions that led up to the Gregorian calendar reform that was implemented by Pope Gregory XIII in 1582, about 100 years after Copernicus' birth. What we're going to be studying is Copernicus' most famous book. It's called On the Revolutions of the Heavenly Spheres. It, like most other scientific works at the time, and theological works for that matter, were written in Latin. We're reading an English translation of it. Of course, this book was published in 1543, which is the year of Copernicus' death. It's good to keep in mind when you're reading selections from On the Revolutions of the Heavenly Spheres that Copernicus himself did not want to present himself as being some kind of radical who's coming up with a new idea. He's going to be pushing this idea that the Earth is one of the planets that is going around the sun. So he is a heliocentrist as opposed to a geocentrist, which was a largely accepted medieval worldview at the time. Anyhow, he's going to be presenting this heliocentric worldview, but he doesn't want to present himself as a radical. He wants to present himself as a conservative. You'll see this as you're going through the text and reading what he has to say. He really says, I'm not coming up with any radically new ideas here. What I'm really doing is I'm trying to resurrect ideas that had been around since before the time of Aristotle in 300 BC. And he cites in particular the work of the Pythagoreans and some other thinkers who believed that the Earth was one of the planets that's going around the sun. And he's going to argue that this viewpoint was rejected prematurely, and he's trying to resurrect this worldview. It's also good to keep in mind when you're reading Copernicus, and he's going to be arguing that the planets are going around the sun, that this is probably 150 years before Newton's theory of gravity. So Newton wrote his theory of gravity in around 1693, 1700. This is published in 1543. So we're a full 150 years or so before Newton's theory of gravity had been proposed. And so when Copernicus is going to be arguing that the Earth is going around the sun, he doesn't have an explanation for why the Earth would be going around the sun in terms of a gravitational attraction. To be sure, people do talk of gravity at this time, but they mean something very different than Newton and we mean by gravity. They don't think of gravity as an attraction of one mass to another. They think of gravity as simply a heaviness that objects feel when you drop them near the surface of the Earth. So a rock has gravitas, or gravity. It's heavy because it falls down toward the Earth. They do not think of the sun as pulling on the Earth and keeping it in an orbit going around the sun, or for that matter, the moon going around the Earth because of gravitational attraction. That is completely far from their thoughts. So Copernicus is going to have to wrestle with this issue of what keeps the planets and the Earth going around the sun. And this is a difficult issue because, after all, there is not another physical law or reason for them to go around the sun. So he's going to remain fairly conservative. He's going to maintain the Aristotelian physics insofar as he can. That's why his book is called On the Revolutions of the Heavenly Spheres. He, like the Aristotelians and the medievals after the Aristotelians, believed that the planets and the Earth, for that matter, were riding on these enormous celestial spheres around the sun. So think, it's hard to imagine this, but imagine a huge crystalline or some other kind of material, transparent material sphere that the Earth and the planets are embedded in, and they're spinning around the sun, and that accounts for their motion or their orbits around the sun. It's almost like a pebble that's stuck in a wheel that's that's rolling across the ground, the Earth would be like the pebble, and the wheel would be like these crystalline spheres that are orbiting around the sun. So he maintains this view, and that's why this book is called On the Revolutions of the Heavenly Spheres. It won't really be until the 1600s, a little bit kind of between Copernicus and Newton, that people start explicitly rejecting the existence of these celestial spheres. And when we come across the work of Johannes Kepler in a week or so, he is going to explicitly reject the existence of these celestial spheres. And that's a very radical position to take, because then one has to start confronting this issue. If there are no spheres that are carrying the planets around the sun, then why are they doing it? So Kepler is going to be speculating on the cause of the revolutions, or the cause of the rotations of the planets around the sun. And this will eventually lead up to Newton and Newton's theory of gravity. On the page, I guess it's page 130, there is an introduction to this book on the revolutions of the heavenly spheres. It's an introduction to the reader concerning the hypothesis of this work. And this introduction is something that was attached to the beginning of this book that was published in 1543, but it's widely considered that this was not written by Copernicus himself. It was written by someone else. It was widely believed that it was written by a Lutheran theologian and friend of Copernicus's named Andrew Osiander. And this is a controversial introduction because it seems to adopt a philosophy of science that differs quite markedly from the philosophy of Copernicus. And so let me just kind of give you a sense of what is in this introduction. Of course, you'll have read this on your own, but if we jump ahead to, I guess, about the 7th or 8th line down, he says that if, however, they, the readers who read this, are willing to weigh the matter scrupulously or very carefully, they will find that the author of this work, that is Copernicus, has done nothing which merits blame. So he's going to be kind of smoothing over the publication of this and excusing anything that the author might have written that the reader might find controversial. So he's saying that the author here is blameless. And he goes on to say, "For it is the job of the astronomer to use painstaking and skilled observation in gathering together the history of the celestial movements, and then, since he cannot by any line of reasoning reach the true causes of these movements, to think up or construct whatever causes or hypotheses he pleases, such that, by the assumption of these causes, those same movements can be calculated from the principles of geometry for the past and for the present, or for the past and for the future too." So notice what he's doing here. He's saying, what is the goal of the astronomer? And he's saying the goal of the astronomer is not really to seek truth or to find the actual causes of why they do things. Rather, the task of the astronomer, or more generally the scientist, according to this author, the author of this preface, the task of the scientist is not to find the true causes of things, but to come up with hypotheses, to come up with ideas that, if taken seriously, would account for what is observed and would simply allow you to calculate where the planets were in the past and where the planets will be in the future. So, in other words, it's not so important to know why Mars is going to be rising at a particular time on a particular day, or why Jupiter is going to be located in the sky at a particular time 7 weeks from now, as long as whatever hypothesis or the model or the mechanism that the astronomer comes up with allows him to calculate accurately where Jupiter will be 7 weeks from now. That's good enough, and that's all that can be expected of an astronomer. So this is sometimes called an instrumentalist view of science that the author of this introduction is presenting. That is saying that science, astronomy, and science more generally is not about a search for truth, but rather it's simply an instrument that allows you to calculate and predict what's going to happen in the future. This is a radically different view than many scientists in the past, and even many scientists today have. But many scientists today do accept this perspective. This is a very popular perspective that science is not about trying to find out what's true and false, but simply is a method or an instrument for predicting what may or may not happen in the future. So this is the philosophy of science that's being presented here. And I think it's important to note that the reason people think Copernicus did not write this is because later on, when we read selections that we know Copernicus wrote, he adopts a philosophy of science that's very different than this. Copernicus is going to argue that he thinks he's come up with a true ordering and a true account of the motion of the planets. Okay, he goes on, by the way, at the bottom of this page, I guess at the bottom of page 130, he mentions that even, and this is an argument for this instrumentalist view of science, he says even the older theories, such as the Ptolemaic theory, the theory that was advocated by Ptolemy, even that had some ideas that are seemingly absurd or strange, and yet they were able to calculate things, and that was good enough. And the example that he gives is one that he presents as kind of an absurd idea that comes out of Ptolemaic astronomy. One of the ideas in Ptolemaic astronomy is to account for the apparent progressions and retrogressions of the planets with respect to the Earth. So according to the Ptolemaic system, let's suppose this is the Earth, right here. And the planets and the sun are going around the Earth. So let's consider for the moment, let's suppose the sun is out here. And Venus was seen as, and of course the sun is going to be going around the Earth, and Venus also is seen as going around the Earth. I'll draw the trajectory of Venus right here. But it's important to note for an observer who's standing here on the Earth, if they look up at the sun, sometimes they will see Venus going in front of the sun, and sometimes they'll see Venus going behind the sun. And so Ptolemy, in order to account for the apparent progression and retrogression of Venus with respect to the sun, he said that that Venus had to be riding not only on a sphere that is going around the Earth, that was called, by the way, the deferent sphere. You don't have to remember that term, but that's what it was called, this sphere rotating around the Earth. But there was also an epicycle sphere, this one right here, that was called the epicycle. And so Venus, right here, was moving around on this epicycle. And again, this is the Ptolemaic system. And so while the center of the sphere was going around the Earth like this, in addition, Venus was riding on this epicycle, so it was kind of a spiral motion like this as it rode on this deferent, so that it would be able to go in front of and behind the sun. And here's the thing that the author, Andrew Osiander, points out, is that in order to account for the angular elongation, or the apparent angle between the sun and Venus, so if I draw a line right here between the sun and the Earth, sometimes Venus appears up to 40 degrees away from the sun in one direction, and sometimes Venus appears to be up to 40 degrees away from the sun in the other direction. So in other words, Venus exhibits up to 40 degrees of what is called angular elongation from the sun. You're probably aware of this, you just don't realize you're aware of it. Sometimes if you look to the east in the morning, before the sun rises, Venus rises, and it can appear about 40 degrees in the sky ahead of the sun before the sun rises. Then it's called the morning star, by the way. So it's up to about 40 degrees in front of the sun, and then as the sun rises, of course, you can't see Venus anymore because it's too bright out, and then it sets before the sun. Other times, the sun will rise in the morning, and then a little while later, Venus will rise. Of course, you can't see it then because it's too bright out, but then the sun will set in the west, and just after the sun sets, Venus might still be about 40 degrees up in the sky following the sun down. So it can be 40 degrees ahead of the sun or 40 degrees behind the sun. So it can have up to 40 degrees of angular elongation. Now, the point that's being made here is in order to account for 40 degrees of angular elongation using this epicycle theory, the epicycle has to have a certain size. It has to be big enough to account for this 40 degrees of angular elongation, right? So if Venus, if it's 40 degrees on one side of the sun, it would have to be over here on the sphere. And if it's 40 degrees on the other side of the sun, it would have to be over here on the sphere as it's rotating around. Now here's the problem, is that if the epicycle of Venus is that big, then at sometimes it's going to be very, very close to the Earth, and other times it's going to be very far away from the Earth. And in fact, he points out here that in order to account for the angular elongation of Venus, Venus must approach close enough to Earth that its diameter is 4 times larger than its diameter when far from the Earth. So that is when it is at what's called perigee. That means para means close, perigee, g means the Earth. So when it's at perigee, the diameter, let's say, is the diameter from our perspective is large. And when Venus is at apogee, think apo meaning away, think apostles are those who are sent away from Jesus. Apogee means when it's far away from the Earth, the diameter will be small. And the author here mentions that the diameter is going to be 4 times bigger closer to the Earth at perigee than at apogee. But the fact is, if you look at Venus in the sky, its diameter is never 4 times as big than at another time. So there's a problem here. There's a problem that he's pointing out in the Ptolemaic system. He says there are other problems at the top of page 131. There are other problems that he's not going to address right now. But if you look about halfway down this paragraph, he says that since for one and the same movement, varying hypotheses, either the geocentric or the heliocentric hypothesis, are proposed from time to time as eccentricity or epicycle for the movement of the sun, the astronomer much prefers to take the one which is easiest to grasp. So there you have this criteria, which one is kind of the most sensible. Since more than one system of explanation might account for the same facts, a lot of times the astronomer will pick the one that's simply easiest to understand. And then he goes on to say maybe the philosopher demands probability instead, but neither of them will grasp anything certain or hand it on unless it has been divinely revealed to him. Therefore, let us permit these new hypotheses to make a public appearance among old ones, which are themselves no more probable, especially since they are wonderful and easy and bring with them a vast storehouse of learned observations. So I'd like you to think about this for the moment. He's basically saying here that we can't know anything for certain unless it's divinely revealed to us. And therefore, we should consider all these different hypotheses, whether the geocentric hypothesis or the heliocentric hypothesis. We should weigh them all, because after all, they're all just methods of calculating where things are at what time. Now, I'd like you to ask yourself, do you believe what he's saying here? Do you believe that science is purely about as an instrumental device for trying to predict things, or do you think it's about a search for truth? Would you be willing to adopt the view, as this author is, that you can be certain of nothing unless it is divinely revealed to you?